Hey everyone, welcome back, Chemistry 3120. Today's lecture 22, we're going to look at intramolecular cross Claisen condensations. So we've completed 20 and 21. Okay, so this lecture will actually be probably one of the shorter lectures, and it's really just one problem that we're going to look at in terms of how we can get an intramolecular reaction to work. It's going to be very similar to the approach we use for the aldol reaction, and for the aldol reaction, remember 5 and 6 membered rings are the most favorable. So let's look at this example here. If we treat this with sodium methoxide and ethanol, and then work it up, what is our intramolecular product going to look like? So let's look for stable 5 and 6 membered rings. So we're going to enolyze and then it's going to react with itself. So where do we see acidic protons? So you can imagine you could enolyze here at this position, and then this could react with one of the esters. If it reacts here, 1, 2, 3, 4, that's a 4-membered ring. Not so good. Again, here, also 4-membered ring. If it reacts here, this generates a 1, 2, 3, 4, 5-membered ring. Okay. That's scenario A. Let's look at another scenario. Where do we have another acidic proton? So we do, and if we take this acidic proton, you can imagine forming an enolate here, and if this reacts here, 5-membered ring. Again, if it reacts here, 3-membered rings, not so good. So we can call that scenario B. So let's look at, doesn't really matter, let's look at A first. So if we get A to react, we're going to get this reaction here. I'm not going to go through the mechanism, but you could go through it yourself. Electrons go up, come back down, kick off the OET group. So you're going to end up with some type of carbonyl derivative. So if you do that, your compound is going to end up looking like okay, so that's compound A. All right, so you can imagine 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? If you have trouble with the rings, what I suggest you do is you actually number them on the structure here. So why don't we do that? Since we're calling this 1, let's call this 1, 2, 3, 4, 5. That's our 5-membered ring. If you do that, it's easier to follow where your carbons are. Okay, so the carbon that reacted, the enolate was here. All right, so that's 1. This is an ester, but once the tetrahedral intermediate comes up and then comes back down, you're left with a ketone. That's 2. 3 is this carbon with a methyl group. 4 is this carbon with these 2 esters attached to it, and then 5 is this bridging carbon. Okay, so number your carbons if it's going to help you draw the correct product. And then it's also nice to kind of go back and forth to confirm that this is indeed your product. Very often, students will come close, or students will add or erase a carbon, and simply doing this check will make sure that you get the compound that you want. Okay, if we look at B, let's look the other way, and let's look at one. I'll put these in blue. 2, 3, 4, 5. So let's take a look at what that looks like. Let me fix this. Okay, so we also have a 5-membered ring, and if we label the carbons 1, 2, 3, 4, 5, you can see that it matches with the blue numbering that I've used there. Okay, so another 5-membered ring. So you have 2 different potential products, right? So which one is going to be your major intramolecular cross-Claisen condensation product, right? Which one is it? Is it going to be A or B? And how do we know? Or maybe it's going to be 50-50. Well, what did we remember about these ester condensations? We remember that you got to have that irreversible step to help push that reaction, right? And that was when you had an alpha proton between the 2 carbonyl groups. So do we have a proton that is between 2 carbonyl groups on either of these molecules? Let's look at A. Okay, so we kind of scan and say, yes, we got 2 carbonyls here, and we have this proton here, which, by the way, will have a pK of around 11 to 13. Okay, so this will, in the mechanism, form a delocalized enolate irreversibly, and then work up, you'll go back to this structure, but that's the driving step. If we look at compound B, if we look between our 2 carbonyl groups here, we don't have an acidic proton. That's a methyl group here. So there's no strongly acidic proton. The best protons that we have are here on this side of the carbonyl, but the pK of these ones are going to be around 20. So there's a big difference between 20 and 11 to 13. So there's no irreversible step here during that reaction. So therefore, this is your minor product, and this compound here is your major product. All right, hope you liked that short lesson on intramolecular Claisen ester condensations. Okay, see you soon for acylation of enols under acidic conditions.